said in the end, just leave it the way it is.
Okay, perfect. All right.
That's why I said microphone.
So, good afternoon, everyone. We're going to resume the program. Hope you all enjoyed your burrito. We're going to pivot a little bit now this afternoon and step away from specific solar technologies to the more integrated issue of how we integrate those technologies into the broader electric system in particular. This panel really has two themes. The first is grid integration in the sense of the generic problems that exist as we bring more and more intermittent renewable type technologies generation to bear. The security issues, the market issues, and so on that arise from those changes. So that's the first element. The second element is a reflection on options, in particular storage options for mitigating some of those challenges, and how that will come together going forward. This was an important issue in the Future of Solar study as well. And as Professor Schmalensee mentioned this morning, we made clear that the future for solar is going to be intimately linked to the future of storage, and that you can't really separate the two. So it's a very important issue to integrate into our program today. We're very fortunate, as always, to have some tremendous expertise here available to us at MIT to discuss this, and that's certainly not, there's no exception on this panel. We have Professor Ignacio Perez Arriaga with us. Ignacio is a professor at Comillas University in Madrid, a visiting professor here at MIT, and perhaps most importantly, he is the leading force in our our Utility of the Future program here at the Energy Initiative, which is exploring many of these topics. We're joined by Saroub Amin. Saroub is a professor in civil engineering and spends a lot of time trying to understand issues regarding system security, grid security, and so on. And that's an emerging topic relevant to this space. And then on the storage side, we're very fortunate to have Yang-Xiao Horn, a professor in material science and engineering and mechanical engineering, and Yepming Chang, a professor in material science and engineering, to bring their very, very deep expertise in this space to bear. So with that, I think we'll just begin by diving straight in and have Ignacio kick things off. And just like the previous panels, we'll have some prepared remarks first, and then we'll have a discussion followed by some questions later.
Okay, thank you very much. Delighted to be here. Frank asked me to prepare 4 or 5 slides. Actually, I have 31. No problem. I have divided my 10 minutes by 31, and I know how many seconds I have to use per slide. So be very attentive. Okay, so I have to talk about grid integration challenges and integration of solar. In particular, I'm going to talk about solar PV or concentrated solar power without storage. Those challenges happen at distribution level or at the bulk power system level. If we focus first on distribution, this is Germany. This is distribution. Just 3 weeks ago, on August 23rd, solar PV plus wind covered 75% of the demand on several hours on a sunny Sunday. 24 gigawatts corresponded to solar PV. In the Future of Solar study, we did some analysis assuming different levels of penetration of solar PV in different parts of the United States. We chose these 6 points. We ran different scenarios for rural, urban, and we got this type of results. What you see here is one of the rectangles that we choose in these locations. We have a model that is able to compute the distribution network that goes to every house, And the dots that you see here are the solar panels that we have sprinkled over the different houses with some method. Then I'm going to increase the number of solar panels, and you will see what happens with the network, which are the lines that you see there. And the green lines that appear are the reinforcements that are needed in the network because of the presence of this penetration of solar panels. So I increase the penetration, and you see more and more of those green areas which are represented here. So more solar panels in the network means that you will have more reinforcements that are needed. If we represent in this figure, in the horizontal axis, the penetration of solar in terms of energy produced by solar divided by energy demanded in that area, and in the vertical axis, which is the cost of the network with the solar panels relative to the cost in the scenario without them, you see that the trend is clearly going up. The different colors correspond to the different places with different quality of the solar resource. Given that we are talking about storage, if we locate in strategic places storage in the distribution network, you can see that the original dots without storage, that are the red ones, become the black ones that have lower costs. So the presence of storage in the distribution network has a value, an economic value, reduces the investment, the additional cost in the network. Of course, that reduction we have to compare with the cost of the batteries, and maybe they will not be viable economically. We have found that in some particular places with current values, they are. Another implication, difficult to explain in a minute, but I will do it. You see on the left this plot that basically is saying that with more level of penetration of solar, the cost for the network users goes up. So let's take that point that corresponds to a certain level, something like 13% of penetration of solar, and this is what the consumers are paying. Okay, if you have what is called net metering, and net metering means that you have a bidirectional meter that turns in one direction when you are demanding energy and turns in the opposite direction when you are producing electricity, injecting that into the network, then what happens is that if you combine that with volumetric tariffs, which is what we typically have mostly in many countries, and particularly in the United States, so the bill that you have, the electricity bill, has a fixed component that is fairly small, typically, and then a volumetric charge. So you pay per kilowatt hour that you consume. Well, with a bidirectional meter, it happens that if you consume during the period of 1 month a certain number of kilowatt hours, but you inject in the network the same value, the meter meters the same thing at the beginning of the period, and then you pay nothing, or you pay the small fixed charge. So what the plot over here says is that with people having typical solar panels, that they don't net out completely the demand, you will, instead of paying that value, you pay less. People pay less. Of course, other people will have to pay more. So this is a pending regulatory problem that could be solved by redesigning the way in which the tariffs for the network are computed currently. The consumers that used to have a typical profile, now with solar PV, plus other, micro cogeneration, electric vehicles, dispersed, local storage, will have profiles that are quite different from one another. And that means that the typical way of designing tariffs is not valid anymore. Let's move now at the bulk power system level. This is the same day in Germany. Well, actually, that day is that Sunday, so this is one entire week. You see the demand of electricity, how much is covered by wind, how much is covered by solar, and in that particular day, in that particular hour, wind plus solar covered 75% of the demand in Germany. Okay, so we have run also some experiments some simulations. This is not an experiment. This is actual behavior of the demand curve in California in 2013, 2015, and well, expected or estimated in 2020. This is what everybody knows is the duck curve for obvious reasons. And so this is the original demand, and this is the net demand after we have that penetration of solar. So we have been modeling the behavior of a system that has some nuclear generation in blue at the bottom that we don't touch it. Then we have coal that we assume that it is typically little flexibility. In operation, we have gas-fired combined cycle gas power plants. And then we start injecting, having solar PV in the system. So you see that part of the demand is being covered by solar PV. We have 2 weeks here. One is typical week of that system in June, and the other one is November. In one, the demand, you can see that the peak demand happens in the middle of the day, and the other one happens in the evening. So we start adding solar, and solar, and solar, and solar, and more solar. And you see that, that big presence of solar is incompatible with having an inflexible generation plant like is coal. This is a very detailed model that includes many of the features of actual power plants. And it shows that, that the peak changes position, that you have much steeper ramps, and that you have new peaks that didn't exist before. This is the time that the sun is rising, the production of solar is growing faster than the demand is growing at that time. What are the possible implications and findings that we obtain from these simulations? Well, one thing that we see is that this curve shows that for higher penetration level of solar, this is the cost, the average cost of production of all the other plants that are not solar. And it goes up. Why? Because solar creates more difficult conditions for the other power plants that have to cycle, have to meet the ramps, have to shut down and start up, and that increases the cost of the thermal generation that accompanies solar. This is another interesting finding, which is if we increase again in the horizontal axis the solar penetration, in the vertical axis we have market prices. And the red curve is the average market price. So we take the average of the 24 hours of the day, and that means that this is the price that would see, the average price that would see a demand that is completely uniform, or a base-loaded generation that is being producing all the time. But what happens is that this is not the price that solar sees. Solar is not present, obviously, the 24 hours of the day. Solar is present only when there is sun. And therefore, the average price that solar sees, so the value of solar, the remuneration of solar, is decreasing the more solar production we have. Because the more solar production we have, at those hours we have less demand, and that demand is covered by less expensive generation units. So that indicates that solar, even if solar is competitive in terms of costs, and it is getting there, will stop by itself, because the more you have, the less remuneration, the less value will obtain from the market. And at a certain point, it will not be economically viable. And I finish with this. This is the impact, again, of storage. So the first curve here is the same one as this one. So the more penetration we have of solar, this is penetration of solar, the less will be the value of solar. What happens if we add storage to the system? Well, that the value of solar increases. So for each one of these points in this line, if we have more storage, solar does have less difficulties, creates less difficulties in the problem. The value of solar goes up, not in very, very much, but goes up. And in the few seconds that I have left, a commercial, well, Frank said that. We are now working. We're in the middle of this project, the MIT Utility of the Future study, and we are addressing many of the problems that we have detected in the future of solar study, such as the design of good tariffs that take into account all this variability, the remuneration of the distribution networks and how that changes, and the regulatory issues associated to that, and many other topics. Thank you very much for listening so carefully.
Thanks, Ignacio. That didn't go as bad as I thought it would, actually, Ignacio. So just one quick question before we move to Sarup. So in Europe, where they have, in Germany, for example, how are they managing the network issues that arise from very high levels of distributed, because they have so much of it at the utility, at the distribution utility level?
Very carefully. So, some people are scared of having large levels of penetration of solar or wind in their systems. Countries like Germany, Spain, Denmark. Actually, it's happening also in Texas, in other places in the United States. It is not that bad. So at wholesale level, you can predict quite well. For instance, solar can be predicted quite well. Right. And then, well, you have to operate the networks and to reinforce the networks accordingly. The problems that solar typically creates are voltage problems, because, you have these reverse flows. Sure. You may not allow the solar penetration to go beyond a certain limit in some places. So, for instance, in Spain, and I think in Germany, beyond a certain limit, you cannot install more until the network is reinforced. And for instance, in Spain, we have a specific control center for renewables. And then we have satellite control centers that curtail, if needed, the renewables if there is any problem. But you can reach very high level of penetration. So it depends very much on the capability of the distribution system operator and the transmission system operator to deal with these issues. And this is done for very large levels of penetration without much difficulty.
There's going to be lots to talk about that in the session. Sarup, yeah.
Okay, so good afternoon, everyone. So Ignacio did a terrific job in setting up the stage on why reliability and economic issues are important for grid integration challenges. My goal here is to convince you of 2 points. First is that as we integrate more solar into the grid, we need to think about better control and monitoring capabilities first. And the second is that we need to proactively think about strategic failures, malicious failures, while we do this integration. So these are the 2 main messages of my talk, okay? So we know that one of the key drivers of the renewable integration is because we are facing problems related to extreme events. One of the reasons is that. And there are more and more weather-related outages, especially in the distribution network. And this is affecting a lot of things. This is affecting utility costs. This is affecting consumers routinely. And we'd like to, let's say, contain that to a certain extent. And one of the solutions, technological solutions, is to use distributed energy resources, solar photovoltaics, and storage devices to try to respond to these kind of reliability issues, okay? And this kind of concerns, not just this one, but other concerns have resulted in the interest in what we call a smart grid, right? And one of the most important aspects of smart grid is, of course, distributed energy resources. Now, to extract full potential of distributed energy resources, we need better control. Better monitoring of the grid, to be able to command the inverters which are associated with the solar panels remotely, okay? And this requires better monitoring and control capabilities on one hand, and direct communication with the substation and the back-end control center on the other hand, right? So this is very important progress from a technological viewpoint. But at the same time, when this kind of progress happens, we have to also worry about new effects, undesirable effects. And these undesirable effects are related to what we call as security threats, cyber and physical security threats, which get integrated also into the grid as the new so-called good functionalities get integrated, okay? And one of the main reasons is that many of the communication technologies and hardware and software which goes into these smart devices is commercial off the shelf. And those vulnerabilities which are there inside these devices also now become part of the grid, okay? And some of these networks are open networks. Even if there are encryption standards, they may not be routinely followed. So these communication networks are prone to false data injection attacks or large-scale attacks by adversaries. And we need to sort of be able to think about this as we talk about integration. So this field of cyber-physical systems is a field which actually permits us to address these challenges from a systems engineering viewpoint. Why? Because it permits us to model both the cyber aspects, the sensors, the actuators, and the controllers, together with the physical dynamics of the grid. And that is the term which I'm going to use, cyber-physical systems, for this integration. Okay? So security attacks are not new, and the goal of today's talk is going to be to promote this kind of thinking as we integrate distributed energy resources. But the prominence came when the Stuxnet attack was discovered. And in 2009, it was released, and it was supposedly perpetrated by more than one nation states against the nuclear program of a certain Middle Eastern country. It was a very sophisticated piece of malware which had specific capabilities to control the enrichment motors out of the control and systematically shut down large number of these enrichment motors in that particular country. And this has resulted in a lot of political and other kind of angers in the current days. Okay, so Stuxnet was not the only attack. There have been attacks of this sort in the past, and I'm not going to go through them. But you can search and find that these kind of attacks are quite prevalent. Okay? So what we are interested in, and this is the focus of my talk, these are the points which I want to keep put forth in front of you, in that when we do this grid integration, we need to ask at least two basic sets of questions. The first is that how can we perform security threat assessment of distribution networks as more and more distributed energy resources are integrated with it? Which of the components are the most critical, okay? How should we get prepared in responding to these failures if they are systematically tampered or attacked? And the second is that how can we utilize better monitoring and control technologies to be able to proactively and reactively respond to these attacks? So the kind of situation which I'm going to focus is was brought up recently by NESCOR report by EPRI. Okay, and this is a very concrete attack situation. So let's focus a little bit here. So the malicious adversary wants to target the communication between substation and the distributed energy resources. So what it does is that it hacks into the communication channels, okay, and introduces some incorrect set points. So using this method, he is able to systematically compromise a large number of PVs, okay? And if it is a high demand situation, it creates an immediate supply demand imbalance in the grid and could lead to voltage and frequency violations. Some loads and other DGs can be disconnected immediately and can result in more such effects where the normal operations won't be resumed unless suitable actions is taken place. And moreover, these kind of effects can cascade into other distribution networks, leading to large-scale effects, okay? So we want to be able to understand and respond to this, okay? So what we are trying to do here is to adopt a game theoretic viewpoint, which means that as network operators or as defenders, what we need to do is to model the objective of the attacker, a strategic adversary, and try to actually consider the effects or impacts of this adversary in order to design our responses, okay? Both before the attack and after the attack. So what we'd like to do is to understand what are the patterns of the worst case attacks that the adversary can perpetrate with specific objectives, okay? What if the adversary is able to compromise a large number of PVs, right, to cause loss of voltage regulation, okay, or loss of frequency, or induce the defender to do load shedding, okay? So these kind of situations may happen, and depending on the objective of the adversary, the attack patterns might look one versus another, okay? So we want to understand what are these kind of attack plans, and we want to be then able to prepare the network operator or the automatic controllers to be able to respond to these situations, okay? By supplying or by triggering other distributed energy resources, or by selectively doing small amount of load control or load management, okay? So that is the goal. So what we found, and these are actually some of the insights from our results, is that similar to Ignacio's presentation, as large number of PVs are targeted. So in his presentation, it's the penetration rate. This is actually the power of the attacker in compromising the PVs. So what we find is that if the defender is able to do a little bit of load control, okay, then in such kind of contingency situations, the voltage regulation can be hugely improved, okay? However, if the load control is very costly, right, if the load control is very costly, then the defender cannot really respond immediately to loss of voltage regulation, okay? So roughly speaking, when you have PVs, the reactive power of the inverters is contributing towards voltage regulation, and the active power, roughly speaking, is contributing towards frequency regulation. So there are two countervailing effects which one needs to balance when such bad situations occur, okay? The second effect is on the load control cost, right? So if the defender is able to control some loads, that is of course costly. So what we observe is that for small intensity attacks, if the number of compromised PVs is quite low, the load control can limit the losses, right? But if the power of the attacker is very high and the large number of PVs are systematically attacked, then the load control cannot really do anything, and you essentially have to live with high costs, okay? There is some saturation effect. So it's not always true that better load control is good in contingency situations such as this. We also have certain theoretical insights. Now, you must be thinking, why is this guy showing me theoretical insights? Well, when we talk about these kind of system theoretic issues, right, our practical designs have to be informed with well-formulated and provable mathematical results. And at least under well-defined assumptions, these results should work and should be then tested in practical situations. So what we find using the physics of power flows and using the optimization methods is that we can try to find out the location of the most critical PV nodes, okay, in the network. And this is in some sense not that intuitive in first go. So what we find is that if the attacker wants to, let's say, induce loss of voltage at node I, what it should do, if it has an option of attacking J or attacking K, what it should do. So what we find is that the attack to node K will induce higher voltage loss to node I, because the path intersection from the substation to I is larger for node K relative to node J. Okay, so it's just saying that the optimal attack plan has some downstream preferences. And this kind of simple result can be used to generate optimal attack plans for a large-scale distribution network. Okay, and we can then find what are the most critical nodes. Okay, so what are the most critical nodes? Why is this important? Because the defender has limited security budget. If I have to invest in IT security solutions, I cannot invest all the PVs. Okay, I have to be strategic in placing the security solutions in a manner which will maximize the effect of my investment. Okay, so there are these two designs. Okay, which of these designs are more secure? Okay, so in one design, design one, the defender secures in a distributed manner. Okay. In the design 2, the defender does security investments in a clustered manner. So what we find is that it is more optimal for the defender to invest his resources in a distributed manner at certain select locations rather than completely securing a part of the grid. Okay? So these kind of prescriptions of security strategies are quite useful for practical purposes. So assume now that the defender has done what it had to do, and now the attack still happened because nothing is 100% secure. The attacks will happen. So defender will have to respond. And how does the defender respond? By firing up other sources of energy or by reducing the load. These are the only two options, right? Perhaps by changing the topology of the grid. So what we find and what we argue here is that instead of doing centralized control of the grid, it is more important for the defender to be able to implement decentralized control policies. What does it mean? Control policies which can automatically detect the presence of the disturbance, okay, one. The presence of the disturbance is detected by local measurements, okay, local measurements only. And then automatic response in a coordinated manner, right, without a central controller. Okay? So what we are trying to do is to design this kind of decentralized control strategies. And let me just try to give you an idea of this strategy. So this is a simple distribution network, and of course the results are generalizable to more complicated networks. So assume that node 3, 1, 5, and 6 are attacked. Okay? So somehow, using local communications, right, what we are able to do is to segment this distribution network into two subclusters or subparts. Okay? One part, which is the upstream part, all those PVs or distributed generators are going to contribute to frequency regulation, okay, by increasing their active power production. Okay? And all those which are downstream are going to contribute to via reactive power for voltage regulation. So this kind of diversification results are very important. Why? Because when we are responding to these kind of contingencies, the DG owners have to be appropriately compensated. Okay? Now they are not going to be happy if they are made to actually produce less active power. Okay, and not being compensated for their reactive power generation. So these kind of diversification effects of this distributed control strategy is very interesting in our opinion from a practical viewpoint. And what we observe is that once these distributed or decentralized controllers are implemented, they are able to bring back the voltage quality and the frequency aspects back to the normal situations immediately after attack. Okay? So in summary, what we have done is to pose the attacker-defender interaction issues in a strategic setting, to have some understanding of what parts of the distribution network, which PVs and which DGs are more critical from a security viewpoint, and how does the defender, okay, how should the defender invest in security solutions, even if he is budget constrained, and after such a contingency is realized, how he can implement distributed control strategies to automatically respond to these contingencies to contain the impact of the attack. Thank you.
Have there been instances of attacks on distributed PV, for example, that have been noted?
Yeah, so if you go to CERT, there is this United States CERT. It's a repository for all the vulnerabilities which are reported. And there are certain instances where the inverters, the software of the inverters is actually compromisable quite easily. There has not been reported attacks, but there has been widespread attacks on the misreporting of the generation and misreporting of the power consumed. So it's not distinct from energy diversion kind of attacks. So these kind of attacks have been reported. Also, there have been attacks on substation devices, physical attacks on substation devices. But by no means one should imagine that cyber attacks are not possible. So these kind of situations are possible.
All right, thank you so much. Professor Shahar?
Great. Thank you.
Good afternoon, everyone. We're going to switch gear and talk about the physical science of energy storage. So we want to utilize electrochemistry to store energy, electricity, because we can actually store quite a bit of energy if we can store the electricity by pumping electrons uphill. And we can store energy, for example, on the level of 1,000 watt-hour per kilogram relative to, for example, very low energy density of pump hydro. So we want to essentially control the energy levels of electrons as a way to store electricity, and we want to change the electron energy essentially by storing the energy in chemical form. So we want to focus on, in this talk, on utilizing oxygen redox as a way to store energy. And the reason we want to utilize oxygen in the picture is it can potentially provide 3 times greater energy storage density relative to conventional lithium-ion batteries. My colleague, Professor Yanming Chang, will provide more details and a general perspective on energy storage technologies, particularly battery technologies. So we're going to focusing on how we can utilize oxygen redox as a way to store electricity coming from renewable sources. So if we look at energy, electricity come from renewable sources. So we can think of storing that electricity in chemical form by split water to produce energy carrier, hydrogen, or lithium, or a metal such as zinc, right, as an energy carrier. And during the process, we actually have oxygen evolution, right? We can also do CO2 reduction and generate small molecules of energy consequence. So once we have these energy carriers, we can utilize them in fuel cells, in batteries, and also in flow batteries, and generate electricity and form water or various rocks or metal oxides or CO2. Right? So essentially, we store the electricity in the left-hand side, and then we essentially produce electricity on the right-hand side, and it's a means to connect the energy generation and the energy demands. So we are interested in utilizing the cycle very efficiently, right? So existing lithium-ion batteries in practice have efficiency, round-trip efficiency, greater than 95%. But if we want to utilize oxygen, even though we can provide 3 times greater energy density, the efficiency is much lower, right? And the efficiency we're typically looking at is 75 or 80%, right? And this is largely, it's really limited by the kinetics of oxygen redox, right? And because we're working with changing oxygen molecules to water or to metal oxides, typically we're looking at multiple electron transfers, essentially controlling the electron energies of multiple electrons. So we've been working with this type of processes for a long time, right, over the last 200 years, from Faraday demonstrating the first water electrolysis and to various demonstration of technologies of fuel cells and metal air batteries, right? And today, and then we look forward towards tomorrow, that we are going really from small-sized fuel cells or metal air batteries. We're gradually implementing the air-based or oxygen-based technologies in larger systems, such as the first demonstration or commercialization of Toyota fuel cell vehicles this year, and to potentially in the future with metal air batteries, and also to make fuel, solar fuel, utilizing photoelectrochemical devices, either involve CO2 or oxygen. So this is really the picture, the overall scheme. One can potentially think of utilizing oxygen for energy storage, right? As we make these devices more efficient and with lower cost, then they become relevant to grid leveling and storage for grid applications. The reason that these devices have very low efficiency, we mentioned that they have very poor kinetics of oxygen redox, right? And this is shown very nicely in the schematic, where if you want to utilize oxygen, and you generate electricity by doing oxygen reduction. This is essentially the energy generation of fuel cell. You have significant energy loss, right, as you drive a current. And similarly, as you pump the energy back in during the storage step, you also have a significant loss. Essentially, the energy loss is shown in the shaded area. And that has to do with the slowness of the reaction associated with essentially a very large barriers or energy barriers associated with converting oxygen to water or to metal oxides, and also reverse the process. So we're very interested in essentially looking at the kinetics and understand what are the general principles, what essentially the rate-limiting step in controlling the kinetics. How can we essentially lower the energy barriers and essentially increase the catalytic activity? And overall, our ultimate goal is to essentially reduce the energy loss associated with utilizing oxygen redox and improve the efficiency of these devices and in turn lower the overall cost of these devices. So one of the compelling approach in search of new catalysts or catalysts with greater activity is really looking at so-called activity descriptor, right? Essentially is you correlate activity for oxygen redox as function of some parameters, right? So you can see for the last 100 years, there's a lot of parameters has been tried, and I only show really a small set of sort of a correlation, right? So you can see these are some of the metal oxide hydroxide bond, and with respect to the binding of oxygen on the surfaces, right? So it's a number of apparent correlation we can draw, right? And essentially we want to determine what is the horizontal axis, right? So that's our control parameter that we want to utilize, right? Because if we know ultimately what control the activity or what control the activation barrier, limit the kinetics, then we can actually utilize that. That's our big knob, and we can actually control the materials and the surfaces to increase activity. So typically, for example, the work that we're looking at is activity in turnover frequency, and these parameters or the control parameters that typically can control the activity by many order of magnitude. Right? So the work has done so far has been looking at really apparent parameters, right? That means that there is some, let's say, bonding strength, which is computed, or parameters that extracted from, for example, the thermodynamic data of the materials. So what we want to ultimately understand what influenced the kinetics is to look at from really the electronic structure of these materials. And we want to essentially looking at the density of states of the electrons, especially near the Fermi level, and line them up with essentially the redox species we're interested in either oxidize or reduce. For example, this line up here, this pointer is running out of batteries, but so essentially, okay, that's great. So this line is actually water reduction line, and then the bottom line is the oxygen evolution, which is the water oxidation line, right? So essentially, first level is you want to line up to the right of density of states as a design of catalytic activity. And what is even, I think, really compelling is you can actually look at these electronic structure and connect with many different reactions. For example, looking at oxygen evolution in the basic solution, oxygen exchange in a solid state oxide-oxide interface for surface oxygen exchange, for CO oxidation or for NOx oxidation, right? And or photoelectrochemical water oxidation, right? So this is essentially, we think, is the holy grail or really the key of connecting various catalytic activities. And I'll show you one example that, in fact, the activity in oxygen evolution basic solutions actually connect with oxygen exchange. And they also connect with essentially the activity for CO oxidation through controlling essentially the surface electronic structure. We can control the amount or the energetics of oxygen vacancies. That is key in catalyzing CO oxidation reactions. So this is one example. We show that if you control the oxygen density of states near the Fermi level, right? If you push the oxygen density state closer to the Fermi level, you can increase essentially the oxygen exchange kinetics. And this is a very important reaction for solid oxide fuel cells. Especially the higher the activity, the lower the losses, and the higher the activity we can make solid oxide fuel cells. And that can be controlled by one parameter. And similarly, if we look at in the basic solution for oxygen evolution, essentially it's the same trend with very similar compound and very different reactions, right? So this just shows at a fundamental level, even though in the experiments we're looking at very different reactions and looking at different electrolytes, and at a fundamental level, it's really the electronic structure of the catalyst essentially influence the catalytic activity. Right? So this is one, essentially the control, and you can also do similar studies and demonstrate how to control essentially the electronic structure to change the degree of CO oxidation and also the degree of NOx reactions. So I want to sort of finish with this particular slide. So in addition to control the bulk electronic structure, you can maintain the same, essentially the bulk catalyst, but you can modify the catalytic activity by several order magnitude, in this case by 2 order magnitude, just by changing the surfaces, by surface decorating with another material less than 1 nanometer thick. Essentially what we're doing here is by modifying the surface electronic structure of the atoms and by introducing essentially segregation of one particular atom to the surface and significantly move the oxygen p band closer to the Fermi level and increase the activity here by 2 order magnitude. So I want to demonstrate, dive into the electronic structure. It's really a key to develop the intrinsic ultimate activity descriptor and allow us to design a catalyst for oxygen-based energy storage technologies that can provide the high energy density much greater than the batteries we have today. And the area that I didn't discuss, but I think is equally exciting, is they can also be very important for developing clean environmental applications, such as we see connections with the catalytic activity to, for example, how surfaces were wet with water or other liquids. So thank you very much.
So today, in terms of the development of these materials, the mechanisms in the lab that is there a very analytical approach that's been taken, or is this a much more empirical effort where you have to kind of cast a broad net in order to identify the opportunity?
Yeah, that's a great question. So in fact, we want to move away from an empirical approach, right? So what we show here is, this is really the study to date, is where researchers are looking at activity and correlate whatever parameters that maybe come from chemical or physical intuition. And moving forward, we're really developing a systematic approach from both understanding the electronic structure and controlling the electronic structure by, for example, spectroscopy. We now know for the first time, really these density states are on the absolute energy scale, and also compared with density function theories, which allow us to experimentally, but also computationally, to validate.
Of course.
And the ultimate goal is to move away from imperial, essentially try and error of catalyst design, but to really develop a rational approach.
Designer batteries, right? That's what we need. Thank you so much. So yeah, man, please. working under pressure. Great, thank you so much.
Thank you. Okay, I'd like to give you a snapshot of where battery technology is today and what we might do to get to lower costs, which you heard earlier this morning is probably the number one parameter, the metric that we care about today. So just to be clear, higher energy density is important because if you have more energy in the same space, generally that translates to lower cost as well, right? So the issue of energy density and cost are not as separate as you might think, right? Very quickly, a couple of snapshots of where this developing battery field is today. This is EVs, the market, and if you don't look at the fine print, it looks pretty good, but if you do look at the fine print, it's 150,000 vehicles versus an annual light vehicle sales in North America of 13 million, right? So, but you know, the slope is positive, right? On the grid side, things actually are ramping up rather quickly too. So this is battery storage. This is storage for grid applications, but only electrochemical storage, right? And here also you see that at this point, we have about 0.6 gigawatts of storage, right? So often units are projected in gigawatts. Underlying this is the fact that the trend now is towards longer duration storage for all the reasons that you'll appreciate thinking about solar, right? And so in terms of gigawatt hours, you might multiply that by, say, 2 or 3, right? But in the future, longer duration storage is really becoming the more important part of the puzzle, right? So a little bit about the EVs, because they've been a significant driver, right? The plot that I have here, the main point here is that there is a lithium-ion roadmap, which is still actually pretty robust. Right? So in some ways today, you know, lithium-ion is the silicon of the battery world. Right? And you see where we are at the bottom here, and with the two largest volume cars in the market today. Oops, switch over. Switch over to the working battery, right? Here we go. Okay, and so the Nissan Leaf, the Tesla Model S. But you know, these bubbles each represent a variation on the lithium theme that has decreasing probability as you go up in energy density, right? And other chemistries that are pretty compelling in a theoretical basis. So this is the theoretical and this is the system level, right, for a known system that you can actually compute the cost of. And you see that, you know, lithium oxygen is absolutely enormous. Here's lithium sulfur, and this is the lithium ion chemistries that I just talked about. Right, so it turns out that because of the emphasis on volume for vehicles, that space has turned out to be more important than weight, right? The EV roadmap emphasizes this scale more. Something like electric aircraft, right? Hybrid electric aircraft would emphasize this axis more, right? But basically, these technologies today, the system level utilization of the energy density potential is still extremely, extremely low, right? And so that's why they are still on the drawing board and not so much in practical use. So the message here is that lithium ion still has quite a ways to go, but you know, why is it so expensive, right? Just to kind of calibrate, because there's been quite a lot in the press about the Tesla Powerwall as an example of stationary storage. These use known lithium-ion batteries, and on a $1 per kilowatt-hour basis, right, if you want to cycle it every day, it costs you more than if you cycle it once a week, because the two chemistries are different flavors of lithium-ion, right? And then if you don't need the pretty packaging and it's simply a storage module that you want to buy as an industrial customer, then this number is about $250 per kilowatt hour, right? So these are just numbers, and let me try to put those in a little bit of perspective here, right? So this is a paper from Nature Climate Change, of all places, and it is a compilation of a large number of cost projections over time, going out to about 2030 here, right? And so what is our actual goal? So first of all, most of these projections, they simply asymptote at about $150 to $200 per kilowatt hour. So in the last decade, there were a number of studies that said we'll never get below $500 a kilowatt hour, and we're far, you know, well below that today, right? But so today, this is what the projections are. And if you were here this morning and heard Tony Bonacisi talk about the goal for PV, 3 cents per kilowatt hour, right? Well, if we can get to $100 per kilowatt hour, right, system level, and get 1,000 cycles out of that battery system, right, then our levelized cost of storage is a penny versus that 3, right? And so at least that starts to feel about right, that the storage doesn't cost more than the generation, right? When I first started working on lithium-ion batteries back in commercializing batteries back in the mid-2000s, we were talking about numbers of $2,000 per kilowatt hour. And I remember a meeting with David Eaglesham at First Solar, and after we started talking about the numbers, as well, okay, let's have a nice lunch and forget about the rest of the proposition. Okay, so things have changed a lot today, right? However, this does not get us to this $100 per kilowatt hour. And in fact, we'd like to get even lower cost than that. There is no lower limit for where we'd like to be. And so what is it that is causing this asymptote, and how do we get there? So let's begin with the chemistry, right? You can't get lower cost of storage than the fundamental chemistry itself, right? And this plot has since 1950 to 2012 or so. And this is in units of dollars per kilowatt hour on a log scale for just the processed material cost. What would it cost you to buy cathode and to buy anode, right? And how much energy is stored. So you cannot get any lower cost than that. And if you want to reach this $100 point, you'd better start off well below that and give yourself some headroom to actually go make the battery, right? And so what you see here are two things. One is that there actually are a number of chemistries that could that start off well below that, and some that are far below that. And so you might ask, well, why does it cost so much to make a battery? Sodium sulfur, high temperature sodium sulfur, basically the sodium and the sulfur are both free, right? But that is the most expensive battery we have for the grid today, $800 a kilowatt hour, because everything else in the system costs so much. Right? That's a real paradox. Right? So the other thing you'll notice here is this upward slope, which is interesting and is a source. It should be a source of embarrassment for people in my field, right? And so the reason for this, and I'll show you later that we are reversing this trend, right, is that this is all in the pursuit of higher energy density for all the things that we like to carry around and now to drive. Okay, so that's why it's been going this direction. But the takeaway is that there are chemistries that you would think would allow you to get to that $100 a kilowatt hour, right? Okay. Lithium ion, as a technology, was developed in the late 1980s and commercialized around 1991. There's an interesting history here. I'll give you the Reader's Digest version of it, which is that around the late 1980s, there was an industry in Japan that was starting to go down the tubes, and that was magnetic tape storage. Right? So reel-to-reel magnetic tape. Think of the last time you used magnetic storage. Right? So what happened was that at the same time, the ascendancy of lithium-ion as a chemistry and physical requirements for thin electrodes, thin coatings, caused the techniques for lithium-ion fabrication, for manufacturing, to be to a large degree derived from magnetic tape. Right? And so reel-to-reel manufacturing methods and the mindset, the knowledge base was transferred over to lithium-ion manufacturing. That's the way we do it today. Right? So my thesis, the thesis of the folks I work with, is that if you knew what we know about lithium-ion today and you set out to produce a lithium-ion battery, you just wouldn't do it this way. Right? And here's a couple of reasons why. In a lithium-ion battery, the one you have in your pocket, right, on your belt, if you take a cross-section of it, in a millimeter of thickness, there are 25 individual layers. Right? Of those 25, 14 do not store any energy, but cost money when you make the battery. Right? And just as one example, there's a separator film, that's the dark line you see here. On an energy basis, that costs you $32 a kilowatt hour. Right? It's a single component. Right? And it's because there are so darn many layers here. Right? And so there's a design problem here. The second problem, I'll talk more about in a bit, is the manufacturing problem. And the making of lithium-ion batteries is tremendously complex, and much more so than it should be. Right? And so these are things that we think we can fix, right? Starting with a clean sheet of paper, but even using the same chemistry. So lithium-ion battery factories are hundreds of thousands of square feet. Right? They're huge buildings. Right? And what you find in them are these large-scale operations. To get into the game today, you have to spend $1 billion, right? And if you spend $1 billion, you can, some would argue that you won't even be cost competitive at spending $1 billion. This plot here is what roughly 20 companies spent, and the ones at the bottom are the ones that are doing well, right? They're the ones that have built the largest plants, right? And so I just want to point out one unit operation here and why a large scale is necessary with the current manufacturing approach. You take an ink, right? It has an organic solvent typically, and you paint this ink of cathode or anode material on a thin metal foil, and then you dry it because in a reel-to-reel process, you can't wind up a wet coating, right? The paint has to dry before you wind it up, right? So if you want high throughput, you have to have a very long drying zone, so you can have high velocity and still enough residence time to dry it. It's as simple as that, right? That drives you to drying zones or factories, coating lines that are hundreds of feet long, and every one of these pipes is an exhaust, it captures the organic solvent that then you recycle, right? Then you take that coating and you calender it, press it under tons per linear inch of pressure. Right? You make a hard, thin coating, and then you cut it, stack it, wind it, whatever, and then at the very end, you put in the liquid electrolyte again, right? So this is, I think this is kind of a crazy process. Why go through all that trouble, right? And so the Tesla Gigafactory is built, at least today, on the same basic model, just simply scaled much larger. And so this is, let's see, this is 35 gigawatt hours, about 400,000 cars per year. And so their idea here is that instead of spending $500 million or $1 billion, we'll spend $5 billion and we'll drive our costs down roughly 25% below everybody else's, right? With the same general approach, right? So what we started working on, and this is now a project that's about 5 years old with a number one, ARPA-E funded, right? First at MIT and then spun out into a company in Cambridge called 24M Technologies, is a completely different way of using the same chemistry. And basically, since you have to use a liquid electrolyte anyway, why not use your liquid electrolyte as your processing solvent, right? Why not avoid drying? Don't even dry. Don't coat, don't dry, just make the battery, right? And so if you take the active materials and you form a semi-solid. Now, this is a snapshot of about 3 years of work, getting all this to work, right? But you can produce a semi-solid, or think of a PACE, electrode, and it turns out that you can make something like this that has all the electrochemical activity of a conventional lithium-ion battery electrode, right? And then, rather than going through all those other operations, just stuff in a cell, right? And this is a cross-section of the two batteries side by side. Externally, they don't look very different, right? But this is 25 layers in a millimeter of thickness, and this is 5 layers dominated by anode and cathode, right? Storage materials, right? And so this is a much simpler way of making a lithium-ion battery, right? So what can you do with that? Well, it turns out that in addition to being a lithium-ion battery that today meets all the requirements for grid storage, right? It has some unusual characteristics, such as this. When we think about wearable devices and conformal devices, you can't do this with a conventional lithium-ion battery. If you take your tablet battery and do that, it'll start to smoke, right? Okay, because those hard coatings will penetrate the separator and create an internal short, right? These batteries, if you take them and feel them, whoever said a battery had to be hard, right? You can actually, you squeeze on it, you'll feel them give a little bit, right? This is a demonstration we do for our friends in the DoD, right? Very abuse tolerant in a different sense, right? And so it turns out that in Cambridge, Massachusetts, this whole approach is being commercialized, and this is we're over here, and this is where 24M. This is south of Mass Ave, Soma, right? And this is a 1 megawatt hour per year, relatively small pilot line. And this is a grid product that's been made, right? So the whole idea here, though, is that this is a different way of making it. You can apply it to any lithium-ion chemistry, right? The numbers, very quickly. The CapEx per throughput is half of that of existing lithium-ion. Instead of at least $500 million, it's a $20 million plant that gets you to the economies of scale, right? And then you simply copy exact, right? And what's the goal here? By 2020, less than $100 per kilowatt hour, right? And so the detailed cost model, the roadmap map to getting there has been at least worked out in concept, right? Okay, I'm going to spend just a few minutes. So that's all about using existing chemistries, which in the end turn out, on a fundamental basis to be nowhere near as bad as we might think, or the press has led you to believe. We just need a better way of making batteries. But on the chemistry side, there's some really interesting things as well, right? So sulfur is something that we will not run out of. I will make the argument here, right? And what is interesting here is that sulfur melts at 113 centigrade. You can melt it on your stovetop, and if there isn't any water around, you'll be fine. If there is, then you'll have to leave the room, right? So what do you do with a low-melting elemental solid like that? Well, you melt and make large blocks, and you stack them like the Egyptian pyramids, and that's what they're doing up in Alberta because of all the sulfur they're producing, right? And so the crane goes up the middle, and you can try to figure out when they'll stop stacking, right? But this is 4 million cubic meters of sulfur, right? Okay. There are a lot of materials that are low-cost materials, but unfortunately, most materials that are low cost don't store any energy. So sulfur is the exception. This is what's great about sulfur, and this is what fascinates me about it. Right? Here's an example. The original lithium-ion battery uses, and still the one that many of you have in on you today, uses lithium cobalt oxide. And if you look at the voltage versus the capacity, this is just charge capacity per gram of the compound, and this is the voltage of the cell using lithium as the reference here. Right? Lithium metal is the reference. The area under the curve here is the energy on a mass basis, so 530 watt-hours per kilogram. Right? So it turns out that sulfur has, look at this, about 4 times the specific energy of a lithium-ion battery. Right? It costs, however, 1,000 times less. Right? And so that's a reason to love sulfur. Right? So unfortunately, lithium-sulfur batteries today don't work very well for a whole host of chemistry reasons that we don't have time to get into. But let's take that last slide and take these 4 million cubic meters of sulfur. And so, nice battery geeky thing to do. How much energy do we have here, right? So it translates to 16 terawatt hours of lithium-sulfur batteries in that pile there, right? So what does that mean? Well, so remember that 13 million light vehicles in North America? Let's take those 13 million vehicles and call every one of them a 85 kilowatt hour Tesla Model S premium version, right? And that's 21 years of supply, right, of the North American fleet, right? So, all right, I'm going to finish right here. I'm actually not going to talk about the details of the chemistry that we're working on, but if you now take this plot and think about sulfur, I've now done an additional thing. I took the cost of the active materials and I added in the electrolyte because it turns out that electrolyte is expensive, right? And so this is, you can't live without cathode, anode, and electrolyte, right? And what this does is to shift the number of these points relative of non-aqueous electrolyte relative to aqueous because water is inexpensive. And it creates a version of this plot with multiple options, shots on goal, that have exceptionally low cost, below $10 a kilowatt hour for this combination of materials. And, well, they don't, I can tell you that this one we've been working on, it only cycles for about 10 cycles right now, so we're not quite there, right? But, if it works, there really is a very attractive future beyond lithium ion, right? So let me stop there. Thank you. Thank you.
So with quite a tight time schedule, so we just have time for 1 or 2 questions. So I'm going to turn to you first, Ignacio. So in light of what we're speaking about today, Solar Day and so on, and really the transformation of the power system to one heavily based on renewables and certainly solar, the question arises, at what point do we have to really begin to think about the large-scale integration of storage onto the grid? You see California today is pushing a significant deployment of advanced storage technologies. is that really needed yet in California? I mean, what are the levels that we're going to have to see in terms of PV penetration, for example, before we have to see this large-scale storage deployment as well?
Well, we have seen that we can reach very large penetration of renewables or intermittent generation without storage.
Right.
There is some built-in flexibility in the power sector. I mean, if you have hydro,
Yeah.
or pump hydro or hydro storage, conventional, you have storage there. Having gas-fired power plants gives you the flexibility also to combine well with the intermittency. So I think that the issue comes to comparing costs, right? So if you have storage, you could have more penetration, reducing the costs of integration in the power system. And depending on the particular power system, the composition, the generation mix, those costs will be different. And therefore, storage will be more or less viable. You could do without storage, but being very expensive. If you have a storage, you could reduce the cost, but you have to subsidize storage. We see in California, we see also in Germany, they are subsidizing residential storage, paying 30% of the investment cost, and you have, I think, 150,000 already batteries installed at residential level. So I think it's a question of which is reducing more quickly, and depends very much on the system. But storage has to be, I mean, when the National Renewable Energy Laboratory and REL made an estimate of what could happen for different levels of penetration of intermittent generation in the US, getting up to 80%, they said, okay, this is perfectly viable, the system could work, but we need storage in large amount.
Right.
So you cannot get to that level without a reasonable amount, a large amount of storage.
So Yip-Ming, in terms of, since you're coming at this from the storage business space, what's your perspective on that?
That's right. You know, if you build a great battery, you have to figure out who to sell it to. Right?
Right.
So, you know, I think that you know, if you take the Tesla Powerwall, you know, when I heard that they were sold out, I was, who are all these people wanting to buy this battery? Because as much as I love batteries, I have net metering, right? And so in Massachusetts, there's no reason for me to, you know, have storage at, you know, for instance, at my house, I have rooftop solar, right? And so there are only a few places in North America where you really can. And, but there are places without net metering. So certainly if you wanted to change policy to push storage, you know what to do there. You know which button to push.
Yeah.
Right?
I mean, actually, perhaps coming back to you, Ignacio, and you, Sarup. So a lot of these opportunities, taking storage, for example, particularly at the distributed level, are going to require a much smarter grid than we currently have. And, you know, how is the preparation going for that? Is that preparation taking place? And then how do they integrate these issues that we discussed about cybersecurity and so on in developing that?
Well, I think in terms of the integration of both the PVs and the storages, the externalities which these newer sources have on the grid have to be taken into account. With or without net metering, if there are actually reverse power flows, this creates additional congestion and deterioration of the infrastructure. And these are long-term effects. So in terms of factoring in the cost, one should also take into account the life cycle of the deterioration and the increased monitoring and control cost needed for the integration of these devices, even without taking security issues into account.
So unfortunately, we don't have time for an audience question because we have a hard stop right now. But what I'm going to do is I'm just going to ask you all to thank our panel very, very much. It's been tremendous, and I'm sure they'll be available for some questions afterwards if somebody has one. Thanks a million. Thanks, Yang. Really appreciate it. I told you we'd be done. So our next panel is going to begin immediately, actually, discussing deployment of storage of solar today.